I have a problem I want you to think about, and I think you can do this without my assistance. Do you remember the problem or the example where I held the book against the wall and pushed the book up the wall using a force that was at some angle? Something like this. Do you guys remember that? Right. In this problem, I want to see if you can just find something out for me. Let's assume the book is 2 kilograms. And let's say I'm applying this force at 45 degrees. How much force do I have to apply so that I don't have to rely on friction to hold the book in place? I would like an answer. In the problem, then you have weight, you have normal force, and you have this applied force. Net force is equal to 0. This one's not hard. This is 45 degrees. So force in this direction. And I know I'm cutting corners. I feel like I'm at a point where we can cut corners, okay? If you're not at a point where you're cutting corners, do more practice. And that means net force in the y direction equals 0. So FA sine 45 equals 20. So my applied force is about 28 newtons. That was it. Again, multiple choice level question. Now, if I push with 30 newtons, the book will slide up, correct? If I push with 25 newtons, the book will slide downwards. So what if there is friction? In fact, what if there's a static frictional coefficient of 0.3? I want you to think about this for a moment. If I push up with more force, there will be a frictional force that will act on the book, correct? What direction? Down, right? It's going to try and prevent the book from sliding up. And if I push with too little force, there's going to be a frictional force as well, right? And what direction will that one be? It's got to be upwards, correct? Those of you who pointed up, thank you for participating. But it's got to be one or the other. So if I don't push hard enough, friction tries to hold the book by pulling up on it. And if I push too hard, friction tries to hold the book in place by pushing down on it. So what's the range? What's the biggest force I can apply and the smallest force I can apply, but still the book stays in place? This is a static friction problem. My force is going to be something plus or minus, but it's going to be around 28. It's going to be a little bit more than 28, or a little bit less than 28. What's the range? It's not centered at 28, by the way. If I start pushing harder, remember the normal force will get bigger, and therefore the frictional force will also become bigger. If I don't push as much, the normal force gets smaller and the frictional force becomes smaller. So 28 is not the midpoint. I want you to find the range. And I've not asked you to do very much more than you've already done in the past. You've done this problem already. You're just doing it twice. If nothing else, set it up. What's the maximum force I can apply, and what's the minimum force I can apply? Draw a free body diagram for each and a net force thing for each. I want to see that you can do this. So again, we're talking about the minimum and maximum force. We know 28 is somewhere in the middle. Gotta hurry. 9 minutes left. We're gonna finish. All right, we have limits on time, so if you just based it on what we did a moment ago, you'll probably have something like this. Now, remember what was asked of you. We're trying to find the maximum force and the minimum force. If you apply too little force, the box wants to slide down. So there has to be an upward force of friction to hold it in place to prevent the book from sliding down. if you apply too much force, in order for the book to stay in place, there also has to be friction. That friction is going to have to point upwards to prevent the book from sliding. So that force is going to have to apply downwards to prevent the book from sliding upwards. The friction changes. And it's on a sliding scale, meaning the amount of friction can be anything up to but including this maximum amount. So if I push just a little bit harder, I get a little bit of friction. If I push even harder, I get more friction. I will reach a threshold. This is a threshold problem. When I'm looking for the max force, I am reaching the threshold. Are you writing anything down on your notes that tell you what it is we're doing at this time, or are you just going to have a whole bunch of arrows and numbers? Because if you don't know what you're doing at this time, then your notes are useless to you again. You're just doing them because I'm sitting here and you're afraid that if you don't write something down, you'll be in trouble. Put something in there. We're looking for thresholds. We're talking about what is the maximum force that you could apply and the book still stay in place, and what is the minimum force. The frictional force is not the same size in each of these two cases because the normal force isn't the same size. But the big difference is direction. The thing about these two problems is that the net force in the x direction is going to look the same. Right? It's going to have the same qualities. Both of these are going to have a component in this direction that's equal to FA cosine 45. They're not the same number, but if I'm just looking at the symbology here, the x direction is going to be FA cosine 45 minus normal equals 0. That will be true for both of them, that the normal force is proportional to one of the components of the force that I'm applying. But in the y direction, I'm going to get two not quite very different, but a little bit different things. I mean, on this side, it'll be FA sine 45 plus friction minus 20 equals 0. All right, friction's upwards. And on this side, FA sine 45 minus friction minus 20 equals 0. I pushed harder, friction's working against me. I didn't push enough, friction is helping me. Now, everything to here, 2 weeks ago we've been doing this. There's nothing new here, except that there's the possibility of the book sliding up or sliding down. Again, this stuff is in your quizzes. But you should be able to tell me how big the maximum force is and the minimum force is. You have enough resources at your disposal to do so. We are at a threshold. At the threshold, the maximum force is when the force is at maximum. So the maximum frictional force will be when this is equal. The normal force is different in both, but the route to solve it isn't. What we've been doing so far this year gets you to here. Now you need to go further. This portion of the problem, well within your capabilities of doing. This is a problem that has 1, 2, 3 unknowns. 3 equations, 3 unknowns. You can do it. Ends up being like low 20s and low 40s. Bell rings before we can finish. You should practice this. And by the way, there's nothing here that couldn't be on your test. I mean, I'm not going to put a threshold question on your test, but the 2 conditions here are first law problems. This level of work is within your abilities for the next test. So you have 2 minutes. Do one of them. Do the work for one of them. Try. Again, if you need it distilled down, this is what we have here. 3 relationships and 3 unknowns. So, I guess, let's see, I'd probably go this way. That friction equals 0.3 times FA cosine 45. First substitution. Then FA sine 45 plus 0.3 times FA cosine 45 equals 20. So FA times 0.707 plus 0.3 times 0.707 equals 20. So FA times 0.919 equals 20. 21.8 newtons. Okay. And the only change to do it for the max is to flip that sign to be negative. If you want to find the other one, the only difference is that sign is negative. So everything will be the same until right here. So you'll have instead FA sine 45 minus 0.3 times FA cosine 45 equals 20. Well, I'm going to do it anyways, only because I'm right here. So 0.707 minus 0.212. So FA equals 20 divided by, let's see, 0.707 minus 0.212. That gives 40. Hold on.